So I'm Tom Beckley, and I lead research and development. Can you hear me? This one doesn't work. Can you hear me? I have to use this one.
And then it's working?
Can you hear me now? That's better. Thank you. So I'm Tom Beckley, and I lead research and development for the custom IC circuit design, simulation, and custom layout at Cadence Design Systems. I have about 600 R&D engineers in my organization across the globe. I'm very pleased to be here at the 5th annual Semiconductor Leaders Forum, and I'd like to thank Dr. Choi and 동부하이텍 for sponsoring this forum and for inviting me. So you know that Cadence is a leading global EDA company and that our customers use software and hardware and services from Cadence to make sophisticated semiconductors and systems. You also know that mobility and social networking and video are key drivers for today's consumers. And these applications are found in personal devices and phones, but increasingly they're found in cloud-based networked businesses, networked homes, and networked automobiles. And successful applications must provide technology integration, high bandwidth, low power, and fast time to market. Those are the keys for success. Our customers are actually analog, right? They are people, so they hear, they touch, and they see. But for their analog functionality, they need faster digital processing. So it's the combination of the two that is very significant. Excuse me. While the examples on this slide are from mobile and low power and automotive, it's true that mixed signal is used in every application, whether it's industrial or aerospace or computing. In the late 1970s, I worked briefly at General Motors. And I remember right before I left there to go to graduate school, I told my departing manager that I felt that in the future, General Motors, an automobile company, would need an electrical engineer at the lead. Because at that point in time, in fact, I worked on a process where we were automating the odometers. So it shows you how unsophisticated it was back then. But today, automobiles have hundreds and hundreds of semiconductors in them, and they control everything from body electronics to engines and transmissions, safety systems, telematics. It's throughout an automobile. And as we were discussing at lunch today, it's not only the electrical content that's heavily mixed signal in automobiles, but it's the software, right? There's millions of lines of code now in automobiles, just like there are in most of your systems today. And the need for validation and verification is really, really important. So everyone here faces a lot of competition. You have to get your products out quickly to market. And if you miss a market window, you quickly lose share. If you miss too many times, you're literally out of business. Who would have guessed 3 or 4 years ago that Nokia and Research in Motion, the makers of BlackBerry, that they would be struggling the way they are today? So we have to compete, and we have to compete effectively. Now, my platform is called Virtuoso, and many of you, I suspect, are users of it for analog mixed signal design. And that allows designers to co-design analog and digital into advanced mixed signal system on chips and designs. So what I'd like to do is talk to you about some of the challenges we see at customers for high performance analog, for mixed signal design, especially in verification, and some of the trends we're seeing in advanced node design. I know many of you may not be at 20 nanometer and below, but I have more than a dozen customers who are at 20 nanometer and below, and I'd like to share with you some of their experiences and some of their findings. Let's start with high performance analog design. So for a circuit designer, robust circuit design is key to high performance analog for high yield and while not sacrificing power and area. Over-design or conservative design is just too expensive today. So you have to have a thorough understanding of your circuit and how it will perform under various conditions or corners. That's very common for analog circuit designers. But increasingly, layout parasitics are becoming more and more important, especially as nodes shrink. So we have re-engineered our entire design platform to try to bring circuit design and layout design much closer together. And we allow something called design constraints, which represent design intent, to be captured early in the design flow for enabling analog IP creation and reuse. To understand the actual circuit parasitics, generally a complete physical layout and an LVS DRC are required. Today, for high-performance analog, most circuit designers use parasitics from a previous design that is similar. This is even changing when we look at layout-dependent effects at advanced nodes, and I'll talk more about that. In traditional design, the link between schematic and layout is mostly done with a layout engineer talking to the circuit designer either through notes or meetings or emails. But if the information is not stored with the design, if it's not stored with the circuit, if it's not stored with the layout, how can you verify accuracy late in the cycle? How could you possibly reuse it if you don't have that design intent stored with the design? So new design flows provide a means for not only capturing the information in one location, but also allow for easy investigation and sharing of that design data across the globe. This concept we call design constraints. So any annotation added during schematic creation, sizing, and simulation of the circuit as constraints helps the layout design team to reduce the number of design iterations. Topologies can be taught to the system even if they're highly crafted. A circuit prospector can go through the schematic, identify topologies, and accelerate design entry. And no coding is required. Constraint verification can simplify design reviews by automatically testing that devices match, that routing is symmetrical, and that high current wire widths are adequate. So concurrent design means as the schematic, connectivity, design rules, and constraints change, your layouts must be updated, and your schematic and your layout must stay in sync. So in the analog circuit design world, we run lots of tests and lots of measurements. And they're run through corners and through process and mismatch variation. My experience has shown that without the ability to effectively manage all of this simulation data, the circuit designer can waste a lot of time. And that is why new analog design verification environments have emerged to manage all of these tests efficiently and to self-document the circuit along with the relevant waveforms. Managing simulations and design reviews becomes much easier as a result. When we examine the more sophisticated analyses needed for robust design and high yield, it can become confusing as to which course to pursue in our goal of design verification. You have to decide what you're trying to do. Are you trying to analyze the circuit, repair, or prevent variation problems? Once you know your goal, it becomes easier as to which approach to take. There are new tools to make this much easier. For example, enhanced Monte Carlo performance using auto-stop and improved sampling methods are now available. Enhanced visualization using CPK, confidence intervals, and quantile-to-quantile plotting help. And high sigma yield estimation with support for worst-case distance algorithms. You can simulate the digital circuitry to calibrate the analog, and then you can simulate the analog. Or to enhance yield and process variation, size over corners, and use worst-case corners to reduce the design space. Let's talk a little bit about physical design of analog. Circuit designers need to quickly get a prototype of a layout in order to understand the impact of parasitics on the circuit. These effects include placement, routing, the use of dummies, and complying with ever-changing and new process rules. To do this, the circuit designer needs what we term higher-level building blocks to quickly get to a floor plan and a placement. We have been investing heavily in building advanced custom building block solutions to enable rapid analog prototyping. In fact, much of this research started at Carnegie Mellon, where I had a spin-out from many years ago. Automatic placement and routing of these complex module generators, or modgens that we call them, needs to incorporate interconnect rules. The solution is constraint-driven from the schematic and keeps the layout and the schematic in sync. The process starts with automatic recognition of basic structures on the schematic. These are synthesized into layouts, then simulated and extracted. The layouts are used in blocks, and the blocks are assembled into a floor plan. The relative placement is saved as a set of constraints, again capturing the design intent. And these enable analog IP reuse and ECOs. Modgens, or module generators, are a place and route environment for creating complex layout structures. In the following examples, you can see different types of device arrays, including highly matched differential pairs and current mirrors. Modgens are built using a common constraint manager, space-based routing, and placement and optimization technologies. Leveraging these core layout technologies provides the circuit designer and the layout engineer with an ideal environment for generating complex array-based layouts that are area efficient and reusable. Once I have my simulation results, the circuit prospector now includes a rapid analog prototyping finder to identify common topologies and to assign automatically design constraints to those topologies. Modgens can be used to quickly realize a physical implementation of a group of transistors that share common functionality and characteristics including dummies, wells, guard rings, power ground, and more. Using modgens, you can quickly get to a good auto placement of the devices in a layout. At this point, you can run device parameter extraction on a layout or continue through routing and actually look at your results in the simulation environment. So we've been partnering over the last 2 years with ST Microelectronics on module generators. I'd like to share with you some of their results. Different structures are captured from the schematic and automatically created in layout. The key is to get to the circuit designer as quickly as possible a real layout. This allows them to take a quick look at their circuit parasitics and potentially layout dependent effects. And as you can see, as you can see, this has about 8 blocks on it. One large one here and then a few more up here. So if you have layout dependent effects, what's key is to keep these distances among the devices consistent. And that is what ST is trying to do here. So you must control the distance between the blocks in order to mitigate the effect of layout dependent effects. Modgens are being used throughout ST now and by the entire back-end PLL clock generation group. They have documented a 30 to 40% productivity saving. It's very significant using this approach. And we rolled this out about 6 months ago, and we have 10 companies now up and running. So if this is of interest to you, please think about it. I'd like to switch gears for a minute. We've seen how to accelerate high-performance analog using the power of constraints, a multi-test simulation environment, new algorithms to improve yield and reliability, and by using the same constraints to drive place and route, which is enhanced when smaller building blocks like modgens are used. But I'd like to talk now a little bit about mixed signal verification. So over 2011 and 2012, we ran a number of technology seminars, and based on more than 500 customer inputs, when asked what is the largest hurdle faced, it was clearly verification of their mixed signal designs. Whether you're designing an SoC for an iPad or an AV chip for a TV or a multi-channel RF chip for a mobile phone, functionally verifying that you haven't made a mistake is a big challenge. And the reason is that verification inside of analog and verification inside of digital are two different things, and they're approached very differently. So where they cross, it is very challenging. And it becomes even more difficult when you add in more and more RF functionality. Mobile data traffic is expected to surge 20-fold over the next 5 years. This is happening in your networked homes, your networked businesses, and your networked automobiles. And this requires designers to incorporate more RF functionality. Mixed signal design gets very tricky as RF content increases. With 4G and 5G, there's an increasing trend to support multiple radios, dual mode Wi-Fi in order to increase throughput. For circuit designers, we like to use SPICE or fast SPICE, but speeding up SPICE won't help where complexity overwhelms the capabilities of a single solution and where analog and digital technology intermingle. Verification is growing exponentially. You need to generate analog blocks in a digital context. You need to validate that behavioral blocks properly account for transistor level specifications. Functional errors, which are very common, can cause major respins. This could be pin connection errors, inverted signals, bad logic, incorrect bus order, connections to the wrong power domain. Very common mistakes, they happen all the time. You need to validate that these are not happening before you spin your first silicon. At lunch, we talked about advanced low power technologies that are unfolding. This results in multi-power domains, and that introduces more and more complexity in the verification challenge. Digital designers have to look into analog, and the same is true for analog designers who have to worry about embedded software that controls their circuit. Therefore, interoperability of digital and analog tools is a must. So how does one approach complex mixed signal verification? Unfortunately, there's no one easy answer. So much of it depends on the product or the system, the design team's knowledge, increasingly on their ability in terms of modeling capabilities and more. The open access database is actually developed by my team, and it's been developed over the last 10 years, is now used commonly throughout the industry. This enables interoperability between digital design and custom design, eliminating the need for left-def, improves design productivity for floor planning, place and route, chip finishing, and integration. An open access flow utilizes a common technology file, a common constraint manager, and a common database. All of those are needed to enable concurrent design. Top-level timing and optimization is enhanced with static timing analysis, speeding ECOs, and minimizing area. Custom views can be stored in the OA database and opened up in a digital tool. Digital views can be stored in the OA database and opened up in a custom tool. That's very important for mixed signal design. Our experience with many, many customers has shown that each company, and in fact different groups within any given company, have different approaches for doing their mixed signal verification. This is a digital-centric approach utilizing long-standing digital verification methods. The analog or digital engineer creates a digital RTL, which is hopefully good enough for the analog and provides sufficient verification coverage and accuracy. Using digital test benches and event-driven hardware emulation, and hardware emulation is very popular these days, is a huge time saver. But what happens if pure Verilog or VHDL, if that model won't suffice? This method uses real number modeling. This is becoming very, very popular. These are in effect sampled waveforms derived from the analog output. In this way, I can add more analog behavior without sacrificing simulation speed were I to use a SPICE or fast SPICE solver. But analog engineers like to work in their custom platform. Here, you can still utilize the speed of real number modeling and use those models to speed up a combination of analog and digital simulation. But one needs good behavioral models in order to do this, and you'd prefer to be able to use them without significant rework across similar designs. There are new tools emerging for enabling these digital blocks and test bench behavioral models. So a top-down approach is getting easier. Not easy, but easier. But the truth is that for many people, they want to use a schematic-driven, deep accuracy, bottom-up approach. And you can still take advantage of all these options, combining fast spice solvers. You can have your critical paths be all analog, and then everything else digital. So there's a lot of choices. I mentioned real number modeling. These constructs have been around for a long time and are represented in the leading digital verification languages. And it's a way in which users can perform verification of analog or mixed signal designs using discretely simulated real values. This allows use of a digital solver versus a spice-based solver and enables intensive verification of mixed signal designs in a short period of time. It opens up the possibility for other techniques like assertions. But real number modeling has been slow for adoption, as it was neither easy nor obvious how to derive the real number model from your analog outputs. So as presented at DAC this year, here's an example of a global mixed signal leader using real number modeling in a digital-centric mixed signal verification flow. The difference between a spice-based approach and an event-driven approach is significant, 300x. So at Cadence, we are pioneering and in fact introducing this month new tools to assist analog circuit designers in automatically building from the schematic behavioral models. So far I've talked about mixed signal verification, but at some point you have to implement your design physically. But how do you get digital and custom layout tools to exchange data seamlessly? We talked about open access already. That's one big part of the equation. And the EDA industry is working to try to make their digital and custom tools work better together. For example, at Cadence, we have a product called Virtuoso Digital Implementation, or VDI, which allows for the layout produced by Virtuoso and the layout produced by our digital tool Encounter to coexist and to understand one another. But inside of Virtuoso, for those customers who have a little bit of digital, they still have to build a physical hierarchy for the digital piece, and that makes it a little bit painful. And so the first major change we're doing is the ability to fully characterize the digital cells inside of Virtuoso, inside of the custom platform, before placing them in the top level of the final design. You don't have to create a digital physical hierarchy, and it makes it easier for engineering changes. You can do in-context optimization, timing-aware schematic-driven layout, and low-power-aware schematic-driven layout. The next major enhancement we are working on is to actually eliminate the Verilog in step, allowing the text to flow through into Virtuoso intact, drive layout creation, and finally transfer to digital for SoC sign-off. While inside the custom platform, the text is alive and not a black box. It can be probed just like a schematic and ultimately drive layout. But you may ask, how do you place sensitive analog and how does it keep pace with noisy digital as the process node continues to decrease? It is well known that analog doesn't scale at the same rate as digital. And this has implications for how best to utilize analog in smaller process nodes. There are a couple of alternatives. You're well aware of them. Analog can be designed at 20 nanometer and below, but it is likely that it will be digitally assisted analog, where calibration and control circuitry is used to minimize the amount of analog. Another alternative is to separate sensitive, larger node analog from noisy digital by using 2.5D and 3D IC approaches, including stacked die and through silicon vias. let's take a look at some of these emerging trends. In my group, we have been on a 20 nanometer journey now for a couple of years, working with leading foundries and leading customers. 20 nanometer design for analog differs significantly from digital. While the analog designer will become more involved with his digital RTL counterpart for the calibration and control circuitry, the reality is that the relationship between the analog circuit designer and the analog layout engineer changes a lot at 20 nanometer. Let me explain that to you a bit. So I just spent, actually about 3 weeks ago, I sat down with a large design team that had just finished a 20 nanometer USB PHY, and they were having a post-design review. They had many, many learnings and a lot of things that they shared, but 2 were very painful results. First, circuit designers must now be very aware of complex physical effects at 20 nanometer and below. More and more verification runs in order of magnitude than they had done in the past are now required. Secondly, physical complexity has exploded. Typically, they had 2 to 3 circuit designers per layout engineer. On this design, they had 3 to 4 layout engineers per circuit designer. That's pretty scary. That's pretty scary. They'd never experienced a design challenge so severe. EDA enablement will help satisfy some of these problems at 20 and 14 and below, but we face significant challenges. Unfortunately, I wasn't here for some of the earlier talks, but I suspect much of this was already covered. There's massive investment cost at advanced node. 20 nanometer and below is painfully expensive. SoC solutions have to have very high volume to justify the investment. Fab costs practically double, true across process, design, and mass costs. In EDA, we spend $1.5 to $2 billion a year on research and development. I would say more than half of that goes for advanced node. It's a lot, a major, major investment. A key challenge, of course, revolves around manufacturing complexity. And this increases design complexity because of new devices, because of new interconnect layers with a multitude of competing and very challenging design rules. From 28 to 20, there are, on average, about 400 new, very complex design rules. Can you imagine your layout designer having to absorb that and keep that in mind as he does his layout? That's why that increase is so significant in terms of the number of layout designers per circuit designer. Circuit parasitics and mismatch in analog become so severe that designers must use more digital control circuitry and calibration where analog used to be sufficient. 20 nanometer transistors are very small and they are very, very fast. Routing and source drain parasitics dominate the design. So we all know that planar transistors at 28 and below 28 nanometer are running out of steam. We also know that a replacement is available, invented more than a decade ago. FinFETs or tri-gates have finally come into play as a way of combating many of the inherent problems with planar transistors. Our experience suggests that although planar transistors may see some people through 20 nanometer, it's actually the FinFET that's going to rule at 14 nanometer or 16 nanometer and below. And for obvious reasons, less power and leakage and the ability to better handle current and frequency. But don't necessarily expect better area on the analog portion of your design. That's far from being proven at this point. For designers, a new axis of variability shows up on the radar. We've been used to process and mismatch variation, which we've handled with corners and Monte Carlo. We are now entering a time where the design is much, much more dependent on the precise layout, where the actual devices and nets land can create layout-dependent effects. And these trends are accelerating at 40 and 28 and 20 and quite severe at 20. No longer can the circuit and the layout be decoupled. There are 2 ways to handle layout-dependent effects. You can spread everything out, right? But that kind of gives up the very benefit of going to a smaller process node. The other is through integrated circuit and layout design, which enables identifying and addressing the effects early in the design cycle. As more custom analog designs migrate to 40 nanometer and below, and believe me, many designs won't go here, but system on chip and many mixed signal designs will go here, circuit design teams need to better handle and manage parasitics. In addition, more layout teams find themselves drawn into the simulation environment to ensure parasitic closure. Why is this needed, you might ask, when many custom analog methodologies already incorporate estimated layout-dependent effects in P-cell device models, device callbacks, and estimated wire models? At advanced process nodes, layout-dependent effects not only have to take into account the separate device and wire effects, but also the effects of devices and wires to their surrounding environment. Anywhere from 20 to 30% of a circuit's performance can be attributed to the effects of the surrounding environment. Two such layout-dependent effects are shallow trench isolation and well proximity. Shallow trench isolation effects for a device must take into account the distance of a gate to each edge of the diffusion, gate-to-gate separation, and the overall length of the diffusion. Think about this. Any handcrafting of devices, folding, merging, abutting, dummy insertion, all impact and potentially impact shallow trench isolation effects and therefore a device's performance. So it gets very tricky. And now you can see why technologies like module generators become increasingly important and why ST is deploying them. However, if we look at the traditional world of custom analog design, we have a gap in the methodology since we have been dependent on having a fully realized DRC clean layout before doing advanced analysis. So in the past, we've made assumptions at the schematic level and generally expect the layout to be within a reasonable tolerance of those original parasitic estimates. Not going to work at advanced nodes, just not going to work. And that's what team after team that I've met with have told me. So what are our choices? In terms of the physical aspect of the equation, you might say analog synthesis. I worked on this for many, many, many years to generate a lot of placements from which to choose, but the reality is you only need one good placement, and you may not get one good placement out of all those alternatives that get automatically generated. We talked about rapid prototyping, and I think that does fit a need, especially at technologies 40 nanometer and above. But I think the real answer that's emerging is partial layout. What if you could incrementally build your physical design and check it for parasitics and layout-dependent effects as you go? Isn't that the right way to approach the problem? You can make sure that each step is the right choice without having to wait until the layout is complete and you have a clean DRC. This approach will yield better results in shorter time. Next year, we're going to introduce this new flow to all of our Cadence customers, whereby we have a real-time extractor and analysis available as the layout unfolds. Where does this fit in the design flow? Right in between our long-standing traditional design methodology. This provides the ability to identify critical problems caused either by layout-dependent effects or by too much IR drop on a net, and can be solved by doing critical placement and routing first and then checking the design instead of waiting for a full layout and DRC LVS. This is what electrically aware design looks like. It is an integrated solution to simulate and visualize physical effects real time. Electrically aware design includes in-design incremental extraction, which allows the designer to see the capacitance and resistance as a route is made. Generally, layout tools have always been geometry-based. The intent here is to make it an electrically based layout tool. With the simulation environment, the designer can simulate using these parasitics and compare the results against specifications. Another unique feature of electrically aware design is the ability to check for current density violations, which would lead to electromigration problems. InDesign extraction and current calculations allow for the real-time visualization of current densities. In this case, green is good. The designer can then look for violations, widen interconnect, or move routes as required. He can then use the new real-time extractor, will recolor the design and show that the electromigration rules have been met. So for advanced nodes, we've looked at new devices, FinFETs, new challenges like layout-dependent effects, and new methodologies to address these challenges. But 20 nanometer is much more. The physics of lithography mean that multiple masks are required for each metal layer, and that design rules become exceedingly complex. I talked about 400 new local interconnect rules. Multiple masks per layer or colors is a difficult challenge for design tools. In the course of design, complex loops can be created that cannot be manufactured using two masks. So the design tools, layout, routing, and design rule checking, need to find and avoid these loops. 20 nanometer has local interconnect routing layers below metal 1 that allow for dense routing. Add in complex abutment, and you have a major change in design methodology. As you can see, 20 nanometer design with local interconnect layers doesn't look like a typical layout in 90 nanometer. Just does not. Each local interconnect layer has defined rules, including orientation rules. Layout, routing, and design rule checking need to be compliant with these new layers, while still allowing for flexible design to minimize area. Due to the challenges of scaling at 20 nanometer and below, we are seeing an increased interest in 2.5D and 3D IC solutions. In many cases, it will be cheaper to manufacture only parts of the design in advanced nodes while using 2.5 or 3D IC to connect the designs in larger nodes. 3D ICs are fabricated using interposer layers and through silicon vias. These are three-dimensional structures with connections through micro bumps. Traditional EDA tools, design, DRC, LVS, and extraction need to understand these three-dimensional structures. The design tools need to provide for alignment of chips that are flipped relative to one another to enable the connection. Comprehensive solutions for 3D IC design are now available. For example, two chips can be visualized and designed at the same time, with one flipped relative to the other. Support is provided for bump creation and alignment between the two flipped chips. In this case, simultaneous editing of the designs is possible. As the bump moves left in the top or mother chip, it will move to the right in the lower or daughter chip. But successful 3D ICs go well beyond design, creating, visualizing, and aligning bumps, as well as reverse side routing and redistribution routing, and extraction using through silicon vias is only the beginning. Thermal and signal integrity effects need to be thoroughly understood and accounted for. Analysis capabilities in the frequency and power domains and in the power grid make this a complex challenge, and testing and reliability is a challenge. Moreover, 3D ICs need to be optimized relative to the various die IOs, the package, the printed circuit board, or chipset. I have a unique opportunity with my 600 engineers to merge technologies into solutions for high-performance analog and for advanced node design and for mixed signal design. My teams work closely with their digital and package board teams to enable SoC solutions for all process nodes. We are accelerating investment in 3D IC because we're seeing a larger demand for it in advanced nodes. Many of you here today are successful Cadence Virtuoso customers, and I'd like to thank you for your business. It has been my privilege to work with so many leading global Korean companies over the years. My first trip to Korea was actually in 1984, so I've been here many times. You are leaders in custom analog design, memory design, advanced node design, mixed signal design, certainly in semiconductor manufacturing and complex packaging. So our job in EDA is to ensure that you remain successful despite ever increasing complexity. Thank you, and I can now take questions.